On this roll is a single strand of continuous carbon fiber 1/3 of a mile long, and this is going to change the way we make things forever. But before I show you how, we need to go over some basics, and why not do that while bashing this brand new Notorious? There are two main types of materials in the world, homogeneous materials and composites. This truck's made out of about a 50-50 split. Most of the metal components are going to be homogeneous, but most of the plastic components are going to be composites. The metal and plastic on this truck exhibit very different properties. The metal is very strong, but very stiff, and the plastic is also strong, but quite a bit more flexible. But what exactly is a homogeneous material? What is a composite? And why does it matter? This beautiful billet of 7075 aluminum, while containing multiple elements, is a homogeneous material. And while it consists of about 90% aluminum, 6% zinc, 2% magnesium, 2% copper, and a few other things, they are all mixed evenly at a molecular level at high temperature, meaning that the properties of this material are basically homogeneous throughout. That's where it gets the term a homogeneous material. Something like this carbon fiber sheet, on the other hand, is a composite. A composite combines the properties of multiple different materials to create a new material. This is primarily carbon fibers with a resin to bind them together. And while homogeneous materials are great, composites can create some properties you just can't get anywhere else. And while there are many different types of composites, this glass-filled nylon being one of them, one of the simplest and most common is exemplified by this piece of foam board. This is basically just two pieces of paper glued to a piece of foam in the middle, but it's actually very strong in bending. However, if I rip one of these pieces of paper off, you can see it's very floppy and bends really easily. The foam in the middle also bends fairly easily. And that's because the piece of foam is actually taking the two pieces of paper and separating them. So instead of the paper just bending like you see here, the paper on top tries to stretch when you bend it, and the paper on bottom tries to compress. Of course, paper isn't very strong in compression, but it is very strong in extension. Composites like this carbon fiber, even though they don't have a foam core, work basically the same way. The goal is to get the carbon fibers away from the center of bending so that you actually have them in extension and compression, which is where the crazy stiffness of carbon fiber composites comes from. The actual scientific term for that is known as tension, and it is the tension strength of this single strand of carbon fiber that's going to be the game changer today. Because while carbon fiber is very strong, you typically only really have a couple different ways to use it. You can buy a sheet like this and then cut out what you want. Of course, you're limited in the dimensions of the sheet, and it's very expensive. Or you can create a custom mold like you see here and make your own molded carbon fiber parts, which are even more expensive. And that's where 3D printing comes in. It lets you take a filament like this and create a part like this. These are complex shapes, and they're designed to mount this fan specifically on a brushless motor. And while you could mill these out of a solid block of aluminum, or even cut them out of a solid block of carbon fiber, it would be difficult and expensive to do so. On a 3D printer, once you have the model set up, all you do is send it to the printer, and assuming your settings are right, you get your part, but there are significant limitations. The way a 3D printer works is by squishing out molten plastic in layers, and not only does that create uneven strength in your final part, but because all that plastic has to be squished through a tiny little hole in the end of a nozzle, you're severely limited in what you can actually print with. For instance, even though this is glass fiber nylon, the actual glass fibers in the filament are microscopic because otherwise they'd clog up this nozzle. And while this glass-filled nylon is technically a composite, because of the size of the fibers, it actually acts more like a homogeneous mixture in most ways. And that's been a limitation of pretty much all 3D printers, at least all 3D printers until now. Meet the Fibreseeker 3. This thing allows you to put a continuous strand of carbon fiber into a 3D print as it's being printed, and this completely revolutionizes the way things are made and the strength we can get out of 3D printed parts. Is it going to finally give us the ability to make serious upgrades for parts like shock towers, braces, and yes, maybe even a chassis? I have no idea, but today we're going to find out together. Before we take a look at this machine, I want to let you know it's a prototype. It was sent to me for beta testing. There are about 10 of them in the world, and being a prototype, it's going to act like a prototype. The hardware and software is not finalized, so everything you see here is going to be a demonstration of the technology in its current form, but things definitely will change before the final form is sent out. And of course, as always, I'm making no money off these sales, no affiliate commission. This channel isn't even monetized. I'm just here to share this awesome new technology with you. Speaking of which, let's go check it out. This is the Fibreseeker 3. It has a 300 by 300 by 250 millimeter build area. That falls somewhere between most standard size 3D printers and large format 3D printers. It is a dual extruder printer, meaning it has the ability to print from two different nozzles, though this is a bit of a special setup. On the rear, you can see there's room for two different spools of filament. One of them goes to the right-hand nozzle. It is a direct drive extruder, and the other one goes to the left-hand nozzle. That's a special co-extrusion extruder, and it's used in combination with that continuous carbon fiber. Powering this up, you can see it's got a nice high-resolution touchscreen. The interface looks really good. Of course, this is subject to change, but I suspect it'll just keep getting better. As part of the initial startup routine, we're going to go ahead and let it do its initial initial bed leveling. This does have automatic bed leveling where it maps out the entire surface of the bed. It'll use that to compensate for unevenness when putting down the first layers to make sure those first layers go down really nicely. While it's doing that, they gave me a box of spares, which means we can look at some of the more technical details of it up close. I'm not sure all this stuff's going to come with the production version, but it does give us a unique opportunity. This is the right-hand extruder. If you're familiar with 3D printing and familiar with Bambu Labs 3D printers, this might look familiar because this is a clone of the Bambu Labs P1P extruder. If you're not familiar with 3D printing, the way these work is pretty simple. Essentially, through a set of gears, the filament's pushed into a hole here in the top. There's a little heater right here that heats up this area, which is known as the melt zone. And then after the filament's melted, it gets pushed out through this little nozzle. There's an area right here known as the heat break, and it prevents all the heat being created here from transferring up here and melting the filament before it's ready to be melted. Having the right-hand nozzle be a clone of the Bambu Lab nozzle is a great thing because this is a very nicely designed setup and should work really, really well. Again, though, I do want to mention this is a prototype, so all this stuff is subject to change. These are metal cleaning brushes that are used in the back to keep the nozzles clean. They go along with these silicone wipers. We've got what looks like a small piezoelectric sensor. I'm not really sure where this goes. We'll take a closer look at that in a minute. These are really interesting. They've got a tiny crystal in them, so when you press them together or move them quickly, they make an electric signal. They can also be used in reverse as a speaker. We've got a spare heater cartridge. This is probably for the left-hand nozzle. And then we have the most interesting thing, which is that custom left-hand side co-extrusion nozzle. If you're familiar with 3D printing nozzles, this looks very different, and I'm definitely curious to see how they're using this. You can see it's got a bit of a bevel there and a much flatter profile. This is going to be difficult to see, but on the left-hand side, they're going to be pushing that carbon fiber through as well as the filament of your choice. All right, we've got the calibrations done. I did have to do a few manual calibrations as well. I'm not going to show that because it might not be the same, but let's go ahead and print the included benchy. We're printing this in PETG from the right-hand nozzle. Right now, PETG is the only profile they have, but in theory, we can use any filament we want with this setup. As you can see, it looks pretty good. This only took about 40 minutes, which is fairly on par for most 3D printers these days. There are a lot of features on this that test a bunch of the different functions of a 3D printer, and overall, this one did pretty well, especially given that this is PETG, which tends to be pretty stringy, and there's not much stringing here at all. Overall, this is a really clean result, especially again for a prototype. All right, now let's move on to our first exciting print, and that's this test hook, which is going to use that continuous carbon fiber. And with that, I've had my first failure. I can't get this continuous carbon fiber to stick directly to the bed. I've tried everything I can to get the bed as clean as possible, and it still doesn't really want to stick down. So let's go ahead and try some of this Vision Miner nano adhesive. We'll just put some of this on the plate, and as you can see, it's sticking perfectly now. While this is printing, I want to let you know I've already talked to Fibreseeker about this issue. They're aware of it, and they're working on it, and it probably won't be an issue in the final product. Now, with that complete, this is a pretty interesting end result. This was printed completely with the left-hand nozzle, so this is almost entirely that continuous carbon fiber. To be honest, I'm not sure this is the best test piece, but as a test piece and a hook, let me pull on this. I'm pulling as hard as I can right now. I'm not the strongest person in the world, but that is incredibly strong for how thin it is. I can feel it starting to straighten out right here, but as you can see, this is not a good composite design because there's nothing in the middle. If this was being held rigid in the middle, it would be a lot stronger, which is why I said this probably isn't the best test piece in the world. However, for what it is, that is really impressive. I was able to pull it apart off camera, and you can actually see all those individual carbon fibers in there. Again, this is not something you can do with a normal 3D printer or pretty much any other process. All right, enough included prints. Now it's time to actually make something. This front brace will be an excellent first test because not only is this a simple design, but it's also something that's not super appropriate for normal 3D printing. These ends are constrained by where they mount, so they really can't be any thicker than what you see here. And even with really high-end filament, that's going to be a challenge to make strong enough. To design this is going to be pretty straightforward. We just need to get the full length here, check our constraints here on the ends, check the width, go into Fusion 360, model this up quickly. Then we're going to move it over into Aura 2, which is the included slicer that comes with this 3D printer. From my experience, I don't think this slicer is based on any other program, and that makes sense because of what they're trying to do. Loading this model in, setting a few parameters, and then taking a look at the preview, we can see it's going to run continuous carbon fiber all the way around the edge as well as in the infill. However, before we print this out, we need to calibrate the two nozzles against each other. There's an automatic calibration process that happens here in the back, but we need to fine-tune it. As this test sample prints out, you can see it's printing PETG from the right-hand nozzle and then the continuous carbon fiber from the left. And this is our first look at the result. This is really interesting. A few things to note: the continuous carbon fiber doesn't quite pile up perfectly on top of itself. This is because the carbon fiber is a little bit smaller than the nozzle, and where it ends up in the print isn't exactly the same every time, though it's pretty close. We can also see that we're a little bit high here and a little bit to the left. So I'm going to make that adjustment. We'll print it out again, and we're a little bit closer this time. A little bit more adjustment, print it out again. And as you can see, everything looks pretty close to perfect now. Again, I'm not going to show this process because it's probably going to change by the time the final product is ready. Now we're going to go ahead and print out the front brace. This is obviously going to take quite a bit longer than it would on a normal 3D printer because because it's laying down that continuous carbon fiber. One thing I've noticed is that it lays the continuous carbon fiber much more slowly in a curve than it does in a straight line. And that makes sense because it's having to be stuck down into the print. And as it goes around a curve, that sticking down is going to be more challenging. And here's the final product. You can see the continuous carbon fiber hiding in there in the infill and all around the edge. And I have to say, especially for PETG, this is incredibly stiff. Let me print out a regular one in PETG on my Bamboo Lab printer so we can compare how they feel. Obviously, this is going to print more quickly because it doesn't have that continuous carbon fiber in it. And by more quickly, I mean much more quickly. This took about 4 hours to print. This took about 13 minutes. And the result is very, very clean, but the difference in material property is dramatic. I can barely flex this at all, no matter how hard I try. However, regular PETG bends and snaps pretty easily. Of course, you could print this stronger with more walls and infill, and PETG really isn't appropriate for this particular part. But again, with that carbon fiber reinforcement, it's a completely different animal. And it's important to remember that we can print parts like this with exotic materials as well and the carbon fiber in them, though I think we're going to save a lot of money doing it like this. We'll talk about how much these prints cost in a little bit, but for now, let's get this thing installed and see how it handles some bashing. I'm not gonna go too hard on this because I wanna save the really hard stuff for when we have the shock tower in it. I do expect this brace to be fine. I've made 3D printed braces before and they've held up okay. The brace itself generally isn't under a ton of stress, though it is possible to break them and rip them out of the screws. I don't expect that this will rip out of the screws, and I don't expect it to have any problems whatsoever, so I don't want to break anything else in the car because that's not what this video is about. We're just going to try a few jumps here and then we'll check and see what it looks like. Man, these stock Notoriouses are a lot of fun. All right, let's give it a couple more jumps and then we will check it out and see what it looks like. I really do like this body too. This is the first time I've seen this body, and overall, it looks really good. I thought I liked the other body style better, but now that I've seen this one bashing, I think it's even better. And yeah, this is such a great backyard basher. And taking a look at the front brace, we can see that it held up perfectly. This is no surprise based on how it felt right off the printer. I actually printed another version with a lot more carbon fiber in it in case this failed. Don't worry though, this won't go to waste. We'll do something more brutal to this later on. For now though, let's move on to something a lot more challenging, and that's gonna be a front shock tower. In order to work on it, we need to take these wheels off, and I can't find my 17mm wrench, so this is a great time to try making a tool. I'm just gonna quickly design a 17mm wrench here. I'm gonna put a 1/2-inch socket on the back of it, and then we're gonna go ahead and get it printed out. Hang on though, I went ahead and stopped that first print because obviously this isn't gonna work, and this is an interesting point of how these things print. The continuous carbon fiber is on the outside, but it's not here on the inside where the strength needs to be. And I'm learning that 3D printing this way is a little bit different from normal 3D printing, and it has its own learning curve. So let's go back into the slicer, change a few settings, go ahead and reprint this. I'm seeing some more stringing on this than on previous prints. I think that's because I've had my filament out in the moisture for too long, and that moisture gets in the filament, causes oozing, and that's what's causing these problems. However, even with that, this did complete and the reinforcement's in the right place, so let's see how strong it is. We're just gonna pop it on the... Uh-oh. Well, it turns out I made this outside part a little bit too thick, but I'll let you in on a little secret. I never actually lost my cross wrench. That was a bit of movie magic. However, I do want to see how strong this thing is, which is why we put a 1/2-inch socket on the back. Let's take this out to the garage, put the torque wrench to it, and see what happens. We've got this on a 17mm hex in the vise. First, we're going to try 10 foot-pounds. No problem there. Let's crank it up to 20 foot-pounds. Seems to handle that fine as well. Moving up to 30 foot-pounds. It took that too. Now we'll crank her up to 40 foot-pounds, and it's starting to move, and yes, it broke. And there we go. We finally broke it at 40 foot-pounds. It did click at 40 before it broke though. You can see it just pushed the wall right out here and then flexed the carbon fiber. The carbon fiber itself didn't break. So if we use a stiffer plastic to go around it, PETG is pretty soft. That could have gone a lot further. Even at 40 foot-pounds, that's far higher than I would expect for something like this. And it means you could actually make useful tools if you needed to. Now, if you're having a good time checking out this new technology, make sure you hit that subscribe button to let me know, because this is far from the last cool new thing we're going to be checking out on this channel, and you're not going to want to miss what's coming up. Fortunately, due to a previous project, I've already got a model of this front shock tower, so we're not going to have to create a new one from scratch. And that's good because there's a lot of specific measurements you have to get right for something like this. So now we just load the model into the Aura slicer, get our settings right, and get this thing printed out. While I was setting this up in the slicer, I definitely found a few more quirks of the way this continuous carbon fiber works and how it doesn't work. If you look closely at this finished product, you'll see that there's carbon fiber going around some of these holes, but not others. Talking to Fibreseeker, that's a limitation of the shortest length of fiber they can actually cut out. The cutters above of the nozzle, so there's a minimum fiber length, and if they can't figure out where to put that fiber, then they just don't put it there. I suspect their algorithm will improve over time, and this sort of thing will get better. Even with that though, I have to say, this looks really cool. It's so awesome to see that carbon fiber in there, and this is also very, very stiff. The nice thing about this part is that all these tight tolerances are gonna give us the opportunity to see just how accurate the printer is, and it feels pretty good so far. Though these screw holes, while in the right locations, are a little bit smaller than specified, that's pretty common for 3D printers and something you can accommodate for pretty easily. But the real question is this carbon fiber reinforcement going to be enough to prevent this from breaking during bashing? Let me get the rest of the parts put on it and let's go find out. Now I have enough experience with these 3D printed parts to know if this was a purely 3D printed shock tower, it would break on the very first jump landing. And yeah, it didn't break. That's nice to see. We'll do a couple more easy jumps and then we'll really start testing it out. So far, it just feels like a normal Notorious. Nice and fun, plenty light, lots of power, and overall, a pretty good experience. But now it's time to get serious. Let's do some real jumps, a couple of big crashes, and see if this tower can actually bash. I'm waiting for the crack. So far, so good though. A little bit more power. Oh, right on the front. That might have broken it. But no, it didn't. It's still in perfect condition. Let's keep going. As I'm sure you can tell, I'm kind of holding my breath on this one. PETG really isn't the ideal base material for this kind of thing. And these shock towers, by design, have to be thin. So it's really easy for them to get broken, especially when they're made out of plastic. But again, I've never really tried plastic with carbon fiber in it, so... Oh, this thing lands so good. Looks good doing it too. Still doing well. All right, let's get a couple of front end crashes in. Let's make it a little bit harder than that. I think this thing's gonna take it. I'm sure we'll break it eventually. All right, here we go. Big hit. Oh, right on the front. And still going. All right, guys. We're really gonna have to push this. Let's hurt it. Oh! Still on its wheels and still going. This shock tower might actually survive. I do want to try to break it because I want to see how it breaks though. Right on the front. Oh, it's still going. There is no way a regular plastic shock tower would have survived that. Big hit on the front. I want to try and get it on one tire and get an off camber hit. Kind of hard to do. Oh, it's okay, something broke. And yeah, it broke in a big way, but not necessarily in a surprising way. Where this split apart is the spot that has the least carbon fiber reinforcement. All the infill's up here. There was no reinforcement around these two screws, and so it really only had to break this little bit on both ends. If I designed this again in the future, I would do it completely differently, and it would have a lot more strength between the top and the bottom here. And I suspect it would be a lot stronger, but even this survived way longer than I expected it to. However, the tower-to-tower brace still looks absolutely perfect, so we really have no reason to swap it out for this much stronger part, so how about we try to lift a few thousand pounds with it? Before we do that, I know a lot of you are going to be interested in the intricate details of this printer, so let's go over a few more things. Like I said before, this is about a 300 by 300 by 250 build size. It has a dual-side magnetic PEI sheet. It uses a standard adhesive back magnet underneath. This bed does appear to be mechanically adjustable, though I have not adjusted mine. The printer uses a standard Core XY system. The lead screws for the Z-axis are connected underneath, so this doesn't have independent leveling. The front door is plastic. The lid is glass. Over here on the side is where the continuous carbon fiber goes in. I can't get a good look at how its drive system works, but I suspect it's using two belts squeezed together to move the filament. Around back is where the main filament goes in. The standard nozzle uses a reverse Bowden setup to a direct drive extruder. The co-extrusion nozzle uses a long Bowden setup. Both of these have filament runout detection, but these aren't standard filament runout. They do actually have filament motion detection built into them, so they should be able to detect jams as well. Moving to the print head and taking the cover off, we can get a closer look at how this mechanism works. The right-hand nozzle is lifted and lowered using a mechanism that's actuated when the head moves to the left and right and runs into its end stops. The left-hand nozzle is the co-extrusion nozzle. The carbon fiber goes straight down through the top, and then the filament comes in from the side through a couple of right angles and then out the nozzle. At least on this prototype, both nozzles go up to 320 degrees and the bed goes up to 120 degrees. And whereas this enclosed chamber is not actively heated, that should be good for some pretty serious engineering grade materials. The interface is clean and seems to be high quality. quality. This does appear to be running Clipper in the background. I was able to use the Mainsail web interface and access the webcam. However, I'm not sure about the official support for any of this at this point. All right, with that out of the way, why don't we go ahead and see if we can print up a chassis for this thing. I'm really curious to see if we can actually do it. I've already got the model created, so let's go ahead and start getting this thing printed out. And while that's printing, let's go see how much weight this carbon fiber can actually handle. Okay, the truck we're picking up weighs about 4,000 pounds, so we're gonna be picking up around 2,000 pounds, and it's all concentrated right there in the center. So we're gonna slowly start lifting this. I don't expect it to actually be able to pick the truck up, but I'm curious to see how far it can go and when it breaks. We're definitely taking some good weight off the truck here, but you can see it's really starting to flex. All the weight is still on that bar though, and we are actually almost, and there it goes, okay. Though I have no way of knowing exactly how much weight that held, based on my experience, it felt like it was about halfway up, which means this was probably holding close to 1,000 pounds. And you can see it just shattered right through those carbon fiber strands. Overall, very impressive. And while we were doing that, the chassis finished printing, but you might notice there's something wrong here. This looks a little bit small, and that's because it is. Not quite sure what happened. I checked, and my actual model ended up small, but I'm not gonna reprint this because this took about 11 hours and took a lot of my carbon fiber. Overall, though, this does look pretty good. It's fairly thin, so it is pretty flexible. I'd probably want to use more carbon fiber and, more importantly, a more appropriate base material. But now it's time to talk about the Fibreseeker 3, what I think about it, and if I think it's going to be an awesome game-changing product. And I'm going to say right off the bat, yeah, I do think it is going to be a game changer. Fibreseek isn't the first company to come up with continuous carbon fiber, but they are the first company to come up with it and make it affordable. Companies can and often do make their proprietary materials very, very expensive. According to Fibreseek, this 500 meter roll of continuous carbon fiber is only going to be about 50 bucks, which means this chassis plate, which took about 100 meters, is going to cost about $10 in that continuous carbon fiber. On top of that, you'll have whatever your base material cost is, but usually that's not very expensive. And whereas that seems like a lot of money for something like this, it really isn't that bad. And assuming the production version is able to print with a variety of materials, including engineering grade materials, this is going to give people access to make things in ways they could never have made them before. However, I do want to stress that everything I've shown you has just been off of a prototype. The final version may be completely different, though I suspect it'll be pretty similar. Overall, I had really good luck using this machine. There are a lot of little things that need to be changed, but other than a couple of issues that I had, which were my fault, I didn't have a single print failure. And for a prototype, I think that's pretty impressive. I really do think they're going to be able to reshape the landscape of functional 3D printed parts. And if you want to be a part of that, I think they're going to be firing up a Kickstarter soon. Of course, be aware of all the limitations of Kickstarters before you pledge any money. And once you're done checking that out, why don't you check out one of these awesome videos?